I want to welcome you to the Requirements Working Group August meeting. We are delighted that we're able to bring these two sessions to accommodate global time zones. So it's been really neat to see the kind of audience that we've got. I think I saw Denmark and Singapore, some of the folks that had introduced themselves, so truly reaching a lot of people. We're in for a good topic on artificial intelligence, enhanced requirements for MBSE. A couple announcements before we get started. Wanted to remind folks that if you have any interest in a particular presentation, or if you would like to give a presentation at one of our RWG meetings, we meet monthly, feel free to send your information to me. It's Kevin Orr. But for today, we got our presenter, Katie Fisher. She's a chief engineer at STC. She's leading a team of digital engineer experts dedicated to enhancing the specification of software-intensive systems through MBSE and developing innovative tools to achieve efficiency in system engineering. Katie is currently at the forefront of incorporating artificial intelligence into the system engineering process and toolsets, paving the way for greater accuracy, optimization, and automation of design.
Welcome to AI Enhanced Requirements for Model-Based Systems Engineering. As Kevin said, my name is Katie Fisher. I got my start in simulation and training way back when, and through a early acquisition process that had a model-based systems engineering requirement attached to it. I was exposed to MBSE and SysML and kind of saw the opportunity and got excited about that, and ultimately switched my career path over into the world of model-based systems engineering at STC, where I am the chief engineer focusing on software. About STC, we are a model-based systems engineering services company. I present this slide mostly because I like to paint the picture of how we started into the world of model-based systems engineering services, and our exposure to hundreds of organizations drove us to see an opportunity and a need to also provide digital engineering services. Through that process, we also ultimately saw a need to provide software and infrastructure support, which is another service we provide. And through all of our services across those skill sets, came clear that there was some opportunity to improve some of our day-to-day workflows. And when OpenAI and ChatGPT kind of came roaring into all of our lives a couple of years ago, we started to do some research and development into how we could leverage that technology for our day-to-day workflows and to improve some of the traditional problems that we saw as we approach systems engineering in a digital model-based manner. And that includes the identification of stakeholder needs, the development of requirements, and the incorporation of those requirements into requirements management tools as part of a larger digital engineering ecosystem. And that ultimately led into what I'm here to talk about today, which is something we call intelligent MBSE. What that is a cloud-native suite of AI applications that have been purposely built for model-based systems engineering and digital engineering. And obviously, all of those activities revolve around quality sets of requirements. That's what it is. Intelligent MBSE is the use of artificial intelligence to aid in systems engineering life cycles, spanning that entire engineering V. We have been working for about 2 years to develop this capability, which I'm going to demonstrate today and talk a little bit about the lessons that we've learned and where we think we are going to go and how we think artificial intelligence is going to be here to stay within our engineering workflows. It's been pretty easy to prove that there is definitely opportunity to leverage artificial intelligence to create better requirements, help us trace our requirements better, get to better systems models, and ultimately aid in better and faster verification and validation activities, ultimately allowing us to reap better return on investment in our systems engineering processes. The MBSE challenge and opportunity. Going digital and going to model-based techniques presents challenges. And this is most noticeable at the early phases of design, where we can see this bell curve over here above concept and preliminary design. MBSE is hard. It requires not only talented requirement writers, talented modelers, talented tool users, and even if you have access to that talent, the entire process is time-consuming It can slow down your systems engineering cycle times. And often we see that it lacks quality, accuracy, and effective traceability to provide that value and that return on investment we're looking for in later phases of design. And this is widely understood that the investment early does reap value if done well in later phases of design, but this chart clearly shows opportunity for improvement, as well as reducing risk, fostering better decision making, and ensuring data consistency. We want to get to a point that we can do things early well. That's going to enable better and faster validation and verification, and also provide room for innovation, optimization within our system designs. That really does present an opportunity. So that is going to bring us to the first topic I'd like to speak to today and give a demonstration of, which is intelligent MBSE creations. And this includes the creation of requirements, essentially leveraging artificial intelligence for speed and quality in those early phases of design, everything from analyzing stakeholder needs to writing requirements, analyzing requirements, leveraging them for system designs, specifically model-based systems designs, and laying a foundation for that value that we can gain in later phases of design. This first opportunity I'm going to speak to is a suite of applications that we've incorporated into this platform that we call Intelligent MBSE. And those applications are the creation applications that have been specifically built for speed and accuracy in those early phases of systems engineering life cycles for the content generation into model-based systems engineering environments, and that includes requirement management tools. If we can get to better requirements, better models, better digital artifacts, that is going to lay the foundation for that value gained later in the system lifecycle. The opportunities, or the slide really represents the objective statement for the applications that fall into this creations category. There are dozens here, but I tried to sum up sort of some of the traditional MBSE problems and how we have approached them or created solutions leveraging artificial intelligence for each one of them. Comprehensive data extraction. So we are often given all sorts of textual-based documents, and we have to parse through all of that, identify stakeholder needs, identify requirements, create those requirements, get them into a digital format. That's hard and time-consuming. Quality and accuracy, I'm sure this runs the gamut, everything from handwritten requirements to just poorly handed down requirements from our stakeholders, and then ultimately human error in poor creation of requirements that are lacking correctness or clarity or consistency. Version control is a biggie. We have to be able to understand the effects of change, whether that is stakeholder needs changing, documentation's changing, standards changing. It's difficult to go back and understand change impact. And it's also very difficult to effectively capture traceability to ground truth and maintain that traceability to ground truth, especially in the face of change. Then one of my favorites is modularity and reusability. Inconsistency and incompatibilities, both in our documents, in our requirements, and in our models, can really wreak havoc on our progression into later phases of design. Through some of the customers we work with at STC, we're starting to see a lot of really innovative approaches to modularity and reusability when it comes to requirements, creating libraries of requirements, leveraging past-built systems to aid in trade studies, compare past-built systems and how they have met their requirements or how they have failed to meet their requirements. And we can really only do that if we have good digital representations of that data and we have access to that data. The intelligent MBSE solutions are the AI opportunities here to solution some of these problems. A lot of easy wins. Large language models and generative AI help with pretty much all of these problems. They can obviously digitize and understand documents very quickly, very good at syntactic understandings, and they can also help us persist that digitization of data so we can leverage it more effectively in later phases of design. Natural language processing and generative AI also plays in clearly to that quality and accuracy piece. The disparate data analysis is super helpful if we have to do data comparisons or data analysis, specifically if that data is in different formats or different locations. It's It's very hard for a human to look at two different documents and understand the changes, or even worse, look at a document and requirements that have been extracted from it and try to understand what needs to be updated based on a change to one of those two sets of data, but large language models are great at that. I'm going to talk a lot more about retrieval augmented generation here shortly. Through a process called retrieval augmented generation in our AI applications, we are able to very effectively capture traceability to ground truth. And through the automation of the artifacts that we produce with generative AI, and with that additional traceability that we capture through retrieval augmented generation, we can create very consistent elements. We can automate them into tools, and then therefore we reap the value of being able to query that data, have it in a digital representation, and leverage it for reuse in other systems or later phases of design. So the architecture of what we are doing here started with the Cameo Systems Modeler integration. This is just that. It is simply an integration that allows us to access the applications that reside on a cloud-based platform. These applications are all REST API based, meaning I can integrate with Cameo Systems Modeler, I can integrate with a requirements management tool, and we also have web app capability to sort of present a tool agnostic opportunity to leverage some of these capabilities. Over on the cloud platform, this is currently hosted in an Azure GovCloud instance. So we do have full protection of CUI data built in here through HTTPS and secure WebSocket technology on our endpoints. But within this GovCloud hosted platform, we have the individual applications. I've only spoken about creation so far, but we also have some analysis and some other kind of cool opportunities to connect out to engineering data that resides in other repositories. Each one of them leverages our large language model orchestration services. This is where the retrieval augmented generation comes into play. That retrieval augmented generation process leverages a number of different storage capabilities, the grounding, vector, and graph databases. This is where we have hosted INCOSE standards on how to write a good requirement, the requirement writing guide. We have EARS syntax information. We have SysML best practices. We have example data, examples of what represents a good requirement, what represents a good engineering workflow. We are GovCloud hosted, and all these applications have been very specifically built for model-based systems engineering workflows, or systems engineering really in general workflows. I mentioned that because I said at the beginning of this presentation, we are a MBSE services company. We are not an AI company. I am not out here trying to write the next large language model. I am here to leverage that technology that industry has developed and mold it into these workflows that draw on all of our experience from our systems engineering expertise in a way that can integrate with systems engineering tools and tool sets. That does allow us to be sort of large language model agnostic. We can work with most large language models as long as they conform to the open API standard. That's not the right word for it, but it's escaping me at the moment. Through RESTful API endpoints to communicate them with effectively. We are also cloud agnostic, so we can deploy to other cloud environments through infrastructure as code. And we can leverage other open source or even custom large language models if they provide an API. From a security perspective, we do adhere to the NIST Special Publication 800-171 guidelines, and that is the framework that's necessary to ensure CUI compliance, and that is overseen by our CISO here within our organization. We also comply with the Secure Software Development Framework and have all of the industry best guardrails in place to protect against known attack vendors. Quick look at the API. Like I mentioned, this is a secure API for all of the applications, and it very much staying in line with those NIST risk management framework for responsible and ethical deployment of artificial intelligence. This is a new slide. It's really kind of cool. These are some preliminary calculations we've done on the efficiencies that can be gained when leveraging artificial intelligence for the creation of our requirements, the extraction of them from text, the creation of architectures, and the analysis of requirements. We have worked with hundreds of different organizations, and through some of the metrics that we have available to when we're working with teams that are doing requirements extractions, we are able to go pull a whole bunch of legacy data, and we came out with some averages on how long humans take to do things like extract a requirement from text. That number averaged out to about 3.85 requirements per hour, and we with Intelligent MBSE can do the same at a rate of about 150 requirements per hour. That's actually a scaled number. I don't think I have actually scaled it down enough because I need to allow more time for human AI teaming. But even so, if we can digitally create 1,500 requirements, I scaled it down to 150. Probably need to scale that down a bit more. Regardless, we're still getting an efficiency gain number of somewhere around like 4,000%. Similarly, when we're just extracting directly from structured data, can do that even faster, and we can perform analysis. Humans were averaging the analysis of requirements at about a little more than 1 requirement an hour, and with artificial intelligence, we can get that up to about 40 requirements per hour. So this all averaged out to about 12,000 or closer to 13,000% efficiencies, which, like I said, even if I scale that down by a factor, multiple standard deviations, we're still well over 100 or 500 or 1,000% efficiency gained when using artificial intelligence. So I really do think that there's always going to be skeptics and there's always going to be concerns with artificial intelligence, but it is so powerful that we need to find appropriate ways to harness it and take advantage of some of these efficiencies. So I'm going to jump into first demonstration of MBSE creations. These, again, are those applications for speed and quality in model-based systems engineering content generation. We are going to create requirements from a multimodal ConOps document. I will talk about the grounding information. There is more than just ears grounding. That's a bit of a misnomer on the slide here. And some of the other technologies we use, like few shot examples, and how we then leverage that data to not only create requirements, but also identify architectural elements to start our architecture generation from our requirements as well, thus starting the entire digital thread from a document to a requirement to an architecture, which will span all the way out into implementation, verification, validation, and sustainment. So I'm going to open up Cameo Systems Modeler. I know Cameo Systems Modeler is not a requirement management tool, but for this demonstration, since we are focusing on requirements for model-based systems engineering, we are going to leverage Cameo's requirement capability for the demonstration. I'm going to do 2 demonstrations. They're going to follow similar workflows. Each is going to allow us to select a document and leverage retrieval augmented generation to create our requirements and system architectures. We are then going to be able to relate those 2 things together. So I am going to select generate intelligent requirements from a PDF. I'm going to select a PDF from my PC, and a PDF viewer will pop up here. This document is a high-density automate vertiport concept of operations. It represents a system modernization effort and the ConOps of that mission. I like to use this document because it's very heavily based in text. It does have some other modes of data, tables, and images. And I'm simply going to select parse all pages and ask that requirements be generated into my system model in this package that I have available. As this executes, you'll start to see some statuses pop up here, and you'll see that this has been, it's being returned back to our model-based systems engineering environment in a number of chunks. This is part of those orchestration services that I spoke to earlier. The document has been digitized by the application. It has been analyzed for similar chunks of text. The images have been verbalized, so they can be utilized by large language models. And all of that information has been broken down into 17 different chunks. Each one of those chunks is ran through the retrieval augmented generation process. So what that means is we compare the text in the document to all of that information in the grounding database. So the INCOSE Requirements Writing Guide, the industry best standards, examples of good requirements, and we start to ping on text from the document that is similar or is representative of stakeholder needs and requirements type language. We then form multiple queries to a large language model and ask that we generate shall statements. There's always a lot of questions at this phase of the generation process. In this particular workflow, I like to say we're giving it the full treatment. This is the expensive car wash, if you will. We're going all the way from unstructured stakeholder needs type language, and we are asking that that language be translated into requirement shall text. There are a number of ways that we can adjust this workflow. We can do a pure extraction of language out of that document. So let's say it's a SRD and you don't want to make any adjustments to the language. We can just extract that out for you. If you want to remain very purely consistent with a particular requirement standard, we can do that as well. I almost always get somebody who's going to look at one of these requirements and say, that's not a good requirement. And that's true. We remain as precisely aligned to the stakeholder needs document as possible. And what I mean by that is we're not going to inject suggestive information into these requirements. So if your stakeholder needs document includes the word approximately, the system shall allow approximately 10 aircraft to land per hour, you're likely going to get the word approximately in these requirements. I'm not going to pretend or try to tell you that we are going to extract absolutely perfect requirements. What we are going to do is identify a stakeholder need or identify a requirement, adjust the syntax according to a rules-based set of information on the back end, and digitize that into our model. We then encourage human AI teaming by presenting all of this information to the user in very clear representations. So we have this hot pink icon here indicating this is an AI generated artifact. It has a name. It has the shall statement. Again, full treatment here. We went all the way from kind of stakeholder needs into formal requirement language, but this is presented side by side. Actually, here's a perfect example of what I was just talking about. The vertiport shall have a parking capacity of approximately 12 aircraft. The actual text out of that ConOps document was vertiports are large multi-landing locations with a parking capacity of approximately 12 aircraft. So that language is pulled out explicitly based on the settings that we have for this workflow or this process. But we present that to the user side by side, and we create traceability all the way back to the document itself, the section of the document, and obviously that line directly out of the document. So this is intended to be reviewed by our humans. We still very much rely on our SMEs, and we still very much rely on our requirements experts to take a look at this. We are picking the low-hanging fruit and doing that heavy lifting to accelerate the process and add consistency into this language, add automation into the process as we go. Should we have completed that human AI teaming process, we would want to move on to an architecture generation capability. So if we've gotten through a gateway or requirements review, we can now do the next application in this creations bucket. And this is to create an architecture from those requirements. This speaks a little bit to some of the disparate data analysis capability because we are not only going to pass the concept of operations document, which has lots of additional language and words and context in it, we are also going to pass those requirements themselves to the application. Lou and I were talking about this a few minutes before the webinar that as much as I am a model-based systems engineer advocate, I don't think that we can ever completely get away from words, and I don't think that we can ever completely get away from documents. So I'm really trying to encourage that we appropriately extract information into our digital environments and we maintain our threads back to the documents so that we can always follow those breadcrumbs back to an actual ground truth source of information And this is very useful for compliance assessments later in design, variant design activities if we're going to do tech insertions or we need to do a end of life impact analysis within our system, that we always have this digital representation and nobody ever has to go back and read every single document. We can simply query them and follow those digital threads, but we don't have to throw them out completely. Similarly, I think requirement language is also important. We can have model-based representations of requirements, but sometimes the addition of words is very helpful, even when we have model-based representations of things. The important thing is that we keep them consistent. We can't have a model-based representation of a requirement that contradicts the language-based representation of that requirement. So again, the consistency and automation of these applications is supposed to help solve that type of problem and maintain that tight coupling that we want between any language and any downstream architectural representation of that requirement and how it is ultimately implemented and tested. So we can ensure that we are meeting our stakeholder needs and testing the requirements effectively. While this one is executing, I'm going to hop back over to my slide to discuss a little bit more about the technology that's going on in these applications. So I mentioned both grounding and retrieval augmented generation. If you're not familiar with those, I'm sure you've heard of large language model training or large language model fine tuning. We are using a technique called grounding and retrieval augmented generation. We are, as I mentioned very early, we are a model-based systems engineering company. We are not OpenAI. They have this figured out, as do all of the other large language model providers out there. So there are certain aspects of this technology that are being best left to the experts, if you will. And that kind of tends to be industry standard these days. What we do is we create grounding and retrieval augmented generation pipelines that allow us to best steer large language models to provide us with technologically relevant responses in a format that we desire or demand from them. So what does that mean? Grounding data is essentially a big database of information. Vector databases, indexes of academic texts, examples of good requirements, information on the EARS syntax, information on INCOSE standards. Anything that we can give the large language model to say, this is what a good requirement is, this is what INCOSE thinks a good requirement is, this is an example of a good requirement according to INCOSE or according to EARS. We store all of that and we use it along with some prompt engineering to form a prompt to the large language model that is going to leverage both the text from that concept of operations document as well as responses from the grounding database. And that query will be fused together to the large language model to provide the structured data back to us with the actual requirement text. So we're using the full capability of GPT-4. Probably we'll start using GPT-5 here pretty soon, as well as that retrieval augmented generation process to get those relevant responses back in the form of the stakeholder needs. It is then, as I pointed out, translated through structured data, which allows us to create the automations of the requirements or the models that allows us, as I stated before, to be integrated into other digital engineering requirements and system tooling environments. And it also ensures accurate and reliable data handling so we can create that digital thread all the way back to that document or to the actual line of text in the document. We're in the process of kind of enhancing this into requirements decomposition, requirements derivation, and the incorporation of behavioral and interface analysis as well. So this next application is about to complete here, and it should pop up our architecture diagram. When the requirements were returned, I'd saved a JSON file, and I like to pop this JSON file up. This is the August 19 p.m. JSON representation of our requirements. And I like to show this because I'm sure lots of people have done lots of interactions with large language models through ChatGPT and natural language. And you've probably noticed that you get inconsistent representations of those natural language responses, and you almost never get a source reference with those responses. These particular applications are different. They communicate in a JSON structured language, And through that retrieval augmented generation, we do capture all of that source data within this structured data response. This is what allows us to integrate with any tool because this is very much structured and understandable from a schema perspective, which means it can not only be used to automate into a SysML tool like Cameo, it can be automated into a requirements management tool as well. It could also be extended to be leveraged with other metadata or other specific needs as required. So anyways, back to the demo, our architecture response has returned here. This is a crazy diagram. Nobody would ever really use this. I just show it so that you can see the complexity of the information that was returned in the second response. Instead, I'm going to jump back over to my slide to talk about the next phase of what we're going to do, which is going to be the analysis part of the demo. Okay, so through those creations, we can effectively flatten this curve in the early phases of design. We can inject that speed and quality, and we can kind of break down the barriers to digital adoptions. And when we accomplish all of those things simultaneously, we get this sort of happy little accident that we have allowed for additional time in early phases of design. So we can use our humans now instead of having them create all these models and do all this data entry and parse all of this digital information. We can use our SMEs for better innovation, for better analysis of alternatives, maybe better research on technology options for the implementation space. We can implement things like product line engineering that maybe we didn't have time for if we wanted to do a really comprehensive digital model-based systems approach without the assistance of artificial intelligence. And all those things combined are ultimately going to help us reduce the slope of this MBSE line and gain even more efficiencies in later phases. We're going to move on to the intelligent MBSE analysis now, which are our AI applications that are going to help us gain insights into the artifacts that we created previously. These applications are really gained at insights and understanding of our digital artifacts, and that includes the requirements, the ability to understand them, query them, analyze them, and potentially rewrite or derive and extend information in our stakeholder needs and or requirements. So the analysis traditional problems are just that, the ability for stakeholders to extract information from our models and requirements, the ability to make good decisions, especially when they have to understand data in disparate locations, especially if maybe those textual-based requirements don't match what you're looking at in your model, and you have to decide how to understand that data for solid decision-making. All of this ultimately plays into specialty engineering. So you may have requirements imposed upon you from a safety critical or reliability or cybersecurity perspective. And we can apply all of these techniques to analyze those requirements and how they are going to affect our system design. And ultimately, this is going to get us to better verification and validation, ensuring that we can compare models to requirements, compare requirements to maybe vendor supplied models. So the intelligent MBSE solutions over here, the AI implementations, revolve around persistent data. This is going to allow us to query our documents. Like I said, we don't have to throw them out, but we need to digitize them and make them accessible. Same with our models and our requirement information. We need to have persistent digital representations that we can search and query, and we can do that with natural language, leveraging large language models. All of that is going to be in machine learning ready data stores. That is going to allow us to have all of the information available to do both analysis and decision making, and also those specialty engineering data analyses like we've never been able to before. And then we're kind of really pie in the sky here. We can start to talk about how once we have solid digital representations, good models, good traceability to our requirements, we can start to deploy things like formal methods within MBSE and get into some very advanced analysis of requirements like we've never been able to before. So jumping into the next demonstration of the analysis capabilities, we are going to interact with our requirements and SysML models through natural language chat to help us provide better understanding, easier gap analysis, and generation of things like summaries and documentation. We're also going to look at how we can use the technology from the earlier demonstration to aid in the analysis and rewrite of our requirements, which is very helpful if you're working with legacy systems or poorly formed requirements as a whole. I'm going to create a new diagram, and I will pick the CNSI Communication, Navigation, Surveillance, and Information Infrastructure element that was created. It does have all of that good traceability and understanding built into the AI tag that we've used. We also can show that we were driven to create a CNSI element because there is a requirement for onboard CNSI technology for data sharing. I probably should not have a satisfy. This should be a trace, not a satisfy here. But the important thing is through this application in just a matter of minutes, we are able to analyze this requirement, identify that because of this requirement, we're going to need an architectural element that will ultimately have to be tested to prove that we have met this requirement. And we automated all of that traceability and information into our model. What also happened when this model was created is that persistent machine learning ready representation of all of this data was created on the cloud-based server. So I can start to interact with this data in ways that I have never been able to interact with SysML data before. I can simply say, tell me about CNSI, and I will get a natural language response that is going to describe this element to me. It will tell me the requirements that are associated with it and also give me the source information. I can do gap analysis. So what parts of the system have no associated requirements? So the charging station, the safety area, and the mode C transponder have not been associated with requirements. I can do things like what requirements satisfy a part. The requirement that satisfies the CNSI is the onboard CNSI technology for data sharing requirement. The whole point of this is that we very much want to get our data into digital forms, but not everybody is going to be a requirements tool expert. Not everyone is going to be a SysML expert. Not everyone is going to be a Cameo systems modeler or power user. And we want to enable these digital practices and capture all of this traceability, but be able to consume it in different ways. We can consume it with natural language. We could build out different applications. I no longer have to look at this diagram and understand what all of these colors and dotted lines and filled in diamonds versus not filled in diamonds mean. I can use easily understandable natural language to interact with this data. So interesting, I didn't get a response here. The system does not support searching by requirements. That's actually a feature we are about to implement. I thought they had pushed that through, but I guess not. So right now we are only able to chat with the architecture. We're not able to chat with the actual requirements, but that is coming in our next release of this. Another cool thing we can do with this technology is analyze requirements. So you might have seen earlier that there was some scoring metric information provided back with our requirements. We have a number of means to leverage our grounded large language models and all of that database-based information we have to aid in the objective and subjective analysis of requirements. So I switched over to a different model here. This is supposed to represent the legacy version of the vertiport that we're going through a modernization effort on. And even though there's only 3 requirements represented here, we are in a pretend scenario that the past built system has poor requirements, but we would like to incorporate them into our modernization effort. And obviously we want them to be quality and better written. So leveraging another application here in those grounded large language models, we can ask for a requirement analysis to be performed. This goes through a number of treatments. And when I get my response and regenerate my table, we can see that the requirement score was returned of a 1 because it should be reliable is a terrible requirement. It gives a description of why it's a terrible requirement. It does not express a specific condition or capability, nor does it provide traceability to design elements or test cases. And then it will give a suggested rewrite. In order to ensure system reliability, the system shall operate without failure under specified conditions for a defined period. Another thing we are kind of addressing early on is these applications are what I would call in kind of a released but user acceptance testing phase. So we are trying to capture all of the edge cases, and we are going through real world deployment of this technology to get feedback on these requirements, to also incorporate better rule sets or provide better example data to ensure that we can be as scalable to all user needs as possible. I mentioned that we have deterministic and non-deterministic means of doing that requirement analysis. The first part of that demonstration showed that we are able to persist the SysML data and understand how it is related to requirements, and that is all hosted in a machine learning ready format on our cloud. And also kind of two of the other applications showcased there were the both deterministic and non-deterministic methods for requirement analysis. First, where we're doing scoring, that is a purely software-based analysis. We've developed a rule set based on INCOSE and other industry requirement writing guidance, clear, concise, single subject, anything that we can evaluate with pure software, regular expression, or regex pattern matching to give a very objective analysis of the language in those requirements and calculate a score. I would really actually love if industry could come up with an algorithm or maybe a standard to do this. We did use all of the industry standard rule sets, but as far as weighting and calculation of that final score, that was a rubric that we came up with on our own. And then we use the non-deterministic or large language model assisted applications where we use a large language model to help analyze the requirement and judge it. Large language models as a judge is a very widely applied technique in generative AI and generally very effective. Large language models are very good at analyzing the outputs of other large language models. So that was the technology leveraged in that description of how the requirement could be improved and the generation of a suggestive rewrite. Coming soon to all of this will be persistence of the requirement data along with the SysML. So that last query will be effective. We are also integrating into SysML v2. I don't know if I mentioned it already, but the structured data translation layer that all of this is based on is actually based on the SysML v2 textual notation, which does have a JSON backbone. So our JSON schema aligns with that. So the next set of capabilities, a future-looking set of capabilities, these are the MBSE connections. So this technological foundation that we've built allows access of requirement data and SysML model data through REST APIs, and it allows the creation of AI applications to act on that data. So if we have connectivity to data and other APIs, we can now really effectively break down some of those engineering silos by doing disparate data analysis and connecting that data across other domains. This is the requirements working group. So there are some cool applications here when we get into creation of test cases to aid in better validation and verification and traceability all the way back to our requirements. But this is maybe a topic for a whole other hour-long session. One of the really cool applications here, I mentioned that my focus is software, and I've always struggled with systems engineering to software handoff, as well as the creation of effective software requirements or software component requirements, and being able to trace the implementation of software back to requirement language. It's always really difficult, especially once you get into compiled or binary or embedded software deployment. So we're hoping to solution some really cool applications here that will allow us to do a better job of effectively specifying software from the requirements and systems engineering perspective, and thus streamlining the implementation for the software teams and creating better traceability between those. Right now, it's very much a severed process from once requirements are handed off to software. It kind of takes on a whole world of its own, and we lack that traceability or effective traceability back to requirements. The chat interface will allow you to simply chat directly with your requirements wherever they may reside, understand any of the additional metadata, the source information about those requirements, get to them, just like was shown in the previous demo. Let's talk a little bit about that technology for the persistence of this data. We were able to take multimodal data. We were able to digitize it into a persistent representation and host it on our cloud. This allows us to now query our documents. It also allows us to create requirements and automate them into tool spaces. The capture and persistence of all of that information is stored relationally in a database that we can now access with APIs. I didn't mention this when I was performing the natural language chat, but I'm sure many of you are used to interacting with ChatGPT in a way that you get wrong answers, hallucinations. Ironically, I was listening to a speaker recently who said the reason large language models hallucinate is because they've been trained on everything that is included in Reddit. Reddit, as you probably know, contains all sorts of very false information, and that data is ultimately captured in some of the foundational large language models. They're doing a great job of working on that, and I expect them to solve that problem long before I would ever be able to. But the point is, we don't want any of those hallucinations or that Reddit data to be incorporated in our requirements or incorporated in the responses to those natural language queries. So that natural language chat actually works differently from how you're used to interacting with ChatGPT. What we use the artificial intelligence for is to actually analyze the user query and make a determination of what the user is interested in. The application then selects from a number of software agents that have been developed, and based on the user query, a deterministic software agent is executed on the data that is represented in this database to ensure that the responses provided back in this chatbot are true and representative of data. So, for instance, even though this query failed here, it did not give me a suggestive answer. It basically says, I can't do this because I do not support that type of query. I don't have an agent for that right now. And that's really important for giving confidence in the use of artificial intelligence. There's always going to be people who see one hallucination or see one error in an AI response and sort of reject the technology as a whole. And we are very cognizant of instilling trust and confidence in these responses through those types of guardrails and techniques that we use in anything that's generated. It's really important from a responsible and traceable and explainable deployment of AI, but it's also really important from the digital engineering perspective as well, that we have traceability back to information. Similar to, we want the text in our requirements to match the development of our models. We certainly want any response that is generated with AI to be fully traceable back to an actual element within the model. And just a quick look at our RAG pipeline. I don't have time to go into too much detail on the RAG process here, but there is security baked in every phase, and we do leverage both relevance extraction and re-ranking to further ensure that we're providing the most domain relevant information as possible back out through that structured data layer. To sum all of this up, through better creation of requirements, better consistency within our requirements and automation, we are able to get to better models within the systems engineering, design, and implementation phases, and ultimately reap far more value in the later phases of design when we start to talk about technology insertions, variant system model development, or incorporation of emerging threat deterrent systems that we are going to have this digital, well-traced, quality digital representation of our system to reap all of that value from later. At this time, I would like to allow for questions. Can you ask it to generate the requirement satisfaction matrix in Cameo? So yes, that can all be done through automation. It's not something we've fully implemented right now at this time, but all of that data is there and can easily be produced. These JSON files can be stored locally as log files. That's an option actually in the tool settings. enable response debug logging. So it will save those JSON files down to my environment, but they are also persisted in that database representation on the back end, which allows the chat. I'm configured for a demonstration environment right now, so I'm not showing all of the configuration that goes into this and the different ways a user can interact with the tool, but you can select which models or which set of requirements or which data you would like to chat with through this chatbot. Another feature I didn't show was I kind of glazed over the connections piece of the tool capability because I wanted to focus mostly on the requirements and the impact of requirements, but we also have a comparison mode, so you can configure which types of data you would like to have access to communicate with. If I go into a comparison mode, I'm actually able to compare the model in my legacy architecture, and I can compare it with the model that was generated in the modernization model over here. And this is kind of an example of how we can do those change impact analyses. In this case, I'm comparing two system models, but this can also be performed on requirements if I were to have those requirements persisted on the back end as well. So remove parts, add parts. Produce a source document summary with associated revisions for auditability. From a capability perspective, yes. From an implementation perspective, not at this time. That is something we have on our roadmap. The ability to have kind of a CI/CD pipeline to provide a situational awareness of document versions, change impact of those versions, and give a similar summary, kind of like is shown here, should a new document become available. Or even if it's not a new version of a document, it's a document that might have similar or conflicting information that we can more easily point that out to a user. And that's really important when you get into things like cybersecurity analyses or software safety analyses. A lot of the reason some of those assessments take as long as they do is because there's often conflicting information in the artifacts. So we'd like to weed that out earlier in the design process so that we can get through some of those tedious certification processes later when you have to go back and find a document or find an engineer who can point you to the correct artifact you need for that. Just kind of scrolling through here is the requirements extraction based on the EARS criteria. So the extraction is not based on the EARS criteria. The extraction is based on all of the grounding information available. So those few shot examples, prompt engineering, access to the EARS syntax information is stored in the grounding information, as are the INCOSE guidelines, as are lots of example sets of data. So the extraction is based on a broad understanding of what should represent a requirement or a stakeholder needs statement. And then the generation of the shall statement, that is based on EARS criteria, and we do have a scoring metric that is also based on the EARS syntax. And that's all configurable, though. I was actually just talking, I think it was Lou, earlier about we feel that we have this good technology base, and now we'd like to fine tune it. So I'm really interested in getting into a collaborative exercise on theory behind the best set of requirement writing rules. I know EARS is mostly based on syntax. It's not really addressing correctness in any way. So how can we fuse all of that data to best refine these applications? The format of the extracted requirements is that JSON file. We can work with Excel spreadsheets as well, though. Other modeling tools, it can really be integrated with any modeling tool that provides an API. We do have some partnerships with a lot of the SysMLv2 tool providers, so we will be working on integrations into those tools here very soon. We don't currently really have anyone working specifically in a V2 explicit environment, so we're kind of swimming alongside right now as that need becomes more prevalent. Once the human SME has reviewed or edited or improved the AI generated requirements, is this fed back to the AI platform for it to learn and improve? Sort of. So the applications themselves are not learning in like an unsupervised learning manner. but we do leverage that human AI and review to improve the applications, improve the few shot examples, and improve our regression testing pipelines. We have a number of evaluation metrics that allow us to have quantifiable understanding of quality and coverage and compliance. This is a handful of them here. We kind of developed these for our own regression testing of the applications, but they became valuable to users from a confidence and understanding perspective as well. So I didn't actually show this feature during the demo, but we do capture the regex on the ear syntax analysis here. If we get a bad score back for that metric, we will highlight that to the user and say that it requires attention. If this isn't a good requirement because we have dialed this workflow in to be as tightly coupled to stakeholder needs language as we can be, so therefore we might not get a perfect requirement out of it, but we can also run additional applications to rewrite or to score or to give a quantifiable metric across the whole set. For instance, if you have your settings for the application, your temperature turned all the way down, you're doing an extraction as opposed to a generation, or a generation as opposed to an extraction, and you can run a whole analysis of across the whole set of requirements to get a good idea of what you're working with and how much human AI teaming might be required here as well. How secure is the software? This software is actually GovCloud hosted. It has been through all of the controls of NIST 800-171 for protection of CUI data. It also adheres to all of the NIST secure software development framework as well. It's scanned internally monthly. So at this point, as demonstrated, CUI compliant, firewalled from all internet connectivity outside of the containerized applications. It can be deployed into further secure spaces as needed. Have you timed the import plus the back-end review of the requirements? That's actually a really good observation. Into the workflow, I demonstrated the import and analysis were performed simultaneously. So it's actually a bit slower than doing a pure import. So we could come up with another metric there as well. That 2 requirements per hour metric that I pulled, we have started tracking our programs a bit more comprehensively to sort of cut off at that text analysis and import to a digital tool, requirements management tool or other, to try to get more specific metrics there. But of the, I think, 7 programs we analyzed based on charging hours and numbers of requirements, we did try to account for as pure of an extraction and digitization process as possible. But like I said, I don't think we're ever going to get to an actual perfect metric there, but I can confidently say it is faster. When the document is parsed and the requirement properties are filled in, is the tool populating a standard boilerplate and can it be customized? Absolutely, it can. It was populating a standard boilerplate that we designed to comply with all of the metadata we are most interested in. However, you might have noticed in this demonstration, we populated the documentation for the requirement as opposed to tag values. And that is because this particular model, Zoom, since it was a legacy model, it does not comply with our standard boilerplate. So instead, we use the documentation field as opposed to that profile or boilerplate. But yes, that can be customized as well. Right now, that would have to be done kind of on a one-off basis. We don't have configuration capability to add that in on the fly or at runtime, but it can be done. Requirements should be validated regardless of LLM or human generated. That's absolutely true. It does generate acronyms. I don't have that demonstration running right now, but we actually had an incredibly motivated and smart intern, and he just did some really cool work on glossary generation. And this was actually the output of the demonstration he just gave to our executive leadership on the work he did this summer. He did some really cool stuff with automating acronyms out of textual-based information. And he also did, this is a bit off topic, but it kind of goes to some of the questions on quality and configurability of how we're extracting the requirements. He did some really cool work on the ability to add dynamic prompting into the application. As I mentioned, there were certain settings that were pre-configured for this demonstration. It was very much locked down to only leveraging language in that stakeholder needs document, even if that did sort of get us to a not perfect requirement. But he showed some really cool utility that would allow the user to, in addition, do prompt engineering on the fly, run the requirement extraction endpoint on this document, but please avoid unambiguous language, even if it appears in the ConOps document. Or another dynamic prompt might be only focus on requirements related to cybersecurity. It's not something we've actually worked into our formal applications suite, but I think it's a really cool, groundbreaking capability that we're going to add into these applications that are going to make them much more user configurable. I didn't get into comparison mode with our chatbot, but I spoke a lot to how intelligent MBSE and large language models in general are great at disparate data analysis. So we do offer the ability to compare and contrast. So I actually have this set up to compare and contrast the two different SysML models. In this case, I'm comparing two system architectures. This can be done with requirements as well. So you could provide a pure application and then maybe provide a dynamic prompt as well, and then do a comparison of those requirements, leveraging something like this, or maybe a more purposely built out application that we might add later on.
One more comment in the chat. Is it capable to automatically allocate the generated requirements to mission, stakeholder, system, etc., or assist in the allocation?
Oh, like to the stakeholder itself, like generate the stakeholder?
Like a traceability is the way I read into it.
Yeah, so do create the traceability from a requirement to anything that's generated from it. This is specifically architecture, but we are expanding that to include behaviors and attributes and interfaces. We don't really have stakeholders on the roadmap, but we have use case and stakeholder generation capability. We did kind of deprecate it because we felt that our SMEs actually do a better job in writing use case statements and having a broader understanding of the technology, but maybe that could be worked in.
The question is that you have requirements that apply to the system you're developing. You also have requirements associated with process, and you have requirements against an organization. So requirements against the organization would go like in a project plan, or if it's against a person, it would go into a procedure. Some of the requirements you showed were not necessarily requirements against the system being developed, but against the people developing that system. So from an allocation standpoint, from the source documents, being able to parse those out and allocate them to the proper entity responsible for executing that requirement.
So yes and no. There is a differentiation between domain objects and system objects. So because that document I used was so heavy on stakeholder needs statements, you'll see a lot of things in here like organizational groups or governing bodies, or NASA, is one of them. So in a way, yes, it will identify NASA because there's probably a requirement in there for the oversight of NASA or ISO 2700 series. So we don't explicitly call this an actor or a stakeholder, but it does handle it differently from an architectural element. So it's like a little bit of that capability. So you can see like Federal Aviation Administration is in here as well. And you're going to get that type of data when you're working with such a stakeholder needs heavy document, in addition to actual system capabilities. All right. Well, I unfortunately do have to jump. Thank you all very, very much for your time. I am more than happy to address any additional questions. I'm going to put my email in the chat. If anyone has any very specific questions, please don't hesitate to reach out. I'd be happy to go into further demonstration about what we're working on. And I'd love to understand how this might help you in your day-to-day challenges or use cases that we might have missed in those objectives and where we're going with this as well.
We thank you very much for your time, Katie. A lot of information, really good, and it's really neat to see how fast some of this is going. I know I've got some more learning to do.
Well, thank you so much, Katie, for this enlightening presentation. You guys have put a lot of work into this. This is a topic of interest that everyone has. You can look in the last year, we've had multiple presentations where people are interested in application of AI to developing requirements.
Thank you very much.
Thank you, Katie.